Acids and Bases, Chapter 16. My first lecture is just a condensed little overview about acids and bases, what they are, where we can find them, how to recognize them, and then the second lecture will focus on problems and things that are more relevant to the exams. So you probably are familiar with acids and bases. Acids are corrosive and bases are caustic. And there's lots of stuff out there that has acidic materials in them. Citrus fruit, right, has citric acid. Here's the structure of it. We'll take a look at this in a little bit more detail later. Hopefully you remember from chapter 11, and I do also talk about it in the first semester, some of these organic structures. Just a reminder, we're leaving out the carbons and the hydrogens. We are showing the hydrogens on oxygen, but each corner has a carbon, and carbon always has 4 bonds. So if you only see 2 bonds, you are missing hydrogens. And if you have 4 bonds, like here's 1, 2, 3, 4, you're set. Same with this carbon here. It's got 1, 2, and the double bond, that's 4, has 8 electrons. Just as a reminder, so we're going to be looking at a few of these structures. So yes, citrus, all kinds of citrus fruits have acid, right? You should probably know this. Tomatoes as well as bananas have an acid called malic acid. Here's the structure of it. Vinegar is the product of bacteria or flies that are fermenting fruit, and it can turn into either alcohol, ethanol, or vinegar, which is acetic acid, as shown here. And any kind of fermented foods like sauerkraut, beer, bread have lactic acid. It's basically the bacteria fermenting lactose into lactic acid. And also we have some in our sweat glands, and so sometimes it can be excreted through our pores, lactic acid, right? Some of the different kinds of acids we should be familiar with. Hydrochloric acid and our stomach acid, so that's a really strong acid. I haven't mentioned that yet, but all the acids I have shown so far are weak, right? So shouldn't be a problem when we're consuming citrus fruit. If we were to drink hydrochloric acid, that's different. But of course we have a thick fat layer inside of our stomach protecting us from consuming our flesh, right? Because this would definitely eat up the inside of our stomach walls, but we have that coating, the lipid coating. Talked about carbonic acid already. That's when you pressurize carbon dioxide into water, and it's one of the equilibriums I use is the one between carbon dioxide plus water forming carbonic acid. I use that to explain Le Chatelier's principle, and then hydrochloric acid, which is a strong acid. So we have strong and weak acids, and we'll look at that here in a second. Bases, shifting to bases for now. Household cleaners, bleach. Not all household cleaners have bleach in them, but a lot of household cleaners have ammonia type products in it. We'll look at those in a second. Those are basic. This is a strong base. That's caustic soda here, or lye, or sodium hydroxide should be the name a chemist calls this, which is a strong base. Those are 2 examples of bases. Other bases, yes. Acid reflux. If we have hydrochloric acid and we get acid reflux, we pop some Tums, which is calcium carbonate, so carbonates, and baking soda, which is a hydrogen carbonate. Both of those species are bases that can be used, right? Since the cookie's here, right? So what happens is you have, and this goes back to first semester, if you add an acid to that in a neutralization reaction, you don't just get water, you also get carbon dioxide. And so it's the carbon dioxide that rises. It's a gas, and that makes your batter rise, or and that's why we use baking soda for cooking. Here's a couple of other examples of bases. Caffeine has a base, so that looks, again, we have an organic structure here. This time we have nitrogens, more nitrogens. We have some oxygens here. We'll look at that structurally here in a second. Chocolate has all kinds of different compounds in it, cocoa. And so the dark chocolate has a compound called phenylalanine, and it actually can mimic dopamine, and that's why some people get not really high of chocolate, but it can be quite addictive to have chocolate. But anyway, we'll come back to these structures and take a look at what makes these bases and what makes these weak bases or strong bases as an overview. Well, here we are already. What makes an acid an acid? There are several different definitions. In the second lecture, I'll go into more detail. But if you are able to produce H+, and that's a proton, it can be referred to as a proton, if you can generate those from a species, from a compound such as hydrochloric acid, and hydrochloric acid is very soluble, so it's going to completely break apart into hydrogen ions and chloride ions. Of course, in water, it will attach to the water. You know, you understand that we have a polar bond. This is partially negative, and so the positive cation here is going to attach and form a species called the hydronium ion. And so one of the definitions is chemicals that produce hydronium ions in solution are acids. Another one is species that donate protons. And so in this case, it is the hydronium ion concentration. If this is an aqueous solution, that has to be true as well. It has to be aqueous. And so hydrochloric acid will be completely breaking apart. It produces a lot of hydronium ion and therefore is a strong acid, whereas something like carboxylic acids, and that's vinegar here, a carboxylic acid has this combination of atoms. It has a carbon double bond to oxygen, and these electronegative oxygen atoms pull electron density away from this hydrogen for some of it to break apart. And so this is a weak electrolyte, and it produces a small concentration, less than 5% usually. So speaking of it in terms of equilibrium, right, so that would mean that the equilibrium constant is going to be much smaller than 1, meaning this equilibrium lies very far to the left, and most of it stays as acetic acid and does not produce a lot of H+, and that's what makes this a weak acid. So weak and strong acids, depending if you have the same concentration of the solution. Hydrochloric acid will have a much higher concentration of H+ or hydronium, which makes it a stronger acid. This is a summary of all of these compounds: the citric acid, acetic acid, malic acid from bananas, lactic acid from fermented foods. And if you look at the structures, you will see what I already labeled as carboxylic acid. That's an organic functional group. It's essentially just a combination, a special combination of atoms that leads to weakening of this OH bond. It's not like in water. This bond will never break, and well, I'm not going to say never. I shouldn't say never, but it's not going to break apart by itself, whereas vinegar, this is a weakened bond due to this electronegative atom here. It's going to weaken that and just dissociate a little bit. And so all of these acids here have that combination. Malic acid has 2 of them here. Lactic acid has 1. And citric acid actually has 3 carboxylic acids. So it has the potential to dissociate, even if it's just 5%. But it depends on the equilibrium constant. And that's something we will look at now that you know what equilibrium is, and can calculate concentrations based on equilibrium constants and initial concentrations of acids. For example, we can easily leap into the mathematics of that. So what we have is some sort of R group, meaning some organic junk, bunch of carbon groups, and they can be different. These all here are pretty simple, but what makes them weak acids is this carboxylic acid that I have in the box here. And that will be good to remember for you. So all of those organic acids will have that. Acid summary before I go into bases. They taste sour, right? Tomato, I don't know how sour a tomato is, but maybe. Tomatoes are definitely acidic, right? You might be aware that you're not supposed to cook tomatoes in an aluminum pan because it can actually dissolve aluminum, and aluminum ions are harmful. And so if you didn't know, don't cook tomato sauce in an aluminum pan. Strong acids or weak also, you will dissolve metals. This is nitric acid here, and it's dissolving a copper penny. Of course, copper penny is not all copper, but regardless, any metal will dissolve. Even vinegar will slowly dissolve and consume iron, or it's just going to be very slow reaction. And also, acids conduct electricity. Even the weak acids, which are weak electrolytes, are going to conduct a little bit of electricity. The more ions you have in solution, the more electricity can be conducted. And then acids and bases always react together in a neutralization reaction. And then finally, this is an indicator. It's called litmus paper. And if you hold a litmus paper to an acid, it's going to be pink. And if you hold it to a base, it's going to be blue. And there are other indicators that we will discuss throughout this chapter. What makes a base a base? Okay, so in this case, we are producing hydroxides. Or a base can also be a proton acceptor, which makes more, it's a little bit more inclusive, right? Because if you have something that produces hydroxides, we wouldn't know how. Remember, the phenylalanine and the nicotine, not nicotine, but caffeine had nitrogen centers. They had no OHs, so they're not going to produce OHs from so obviously, but they will actually. It's that lone pair that will grab one of those protons and rip it apart. Here, I just said that hydrogen, that water wouldn't break that bond, but not on its own. I said, but you can rip it off if you have a base that is entering the solution. So here you are getting hydroxide ions, but again, it's 5%. And so any compound, here we have it. Here's ammonia. That's also a household cleaner. You can react any kind of nitrogen that has 3 groups on it. So these can also be replaced with alkyl groups, meaning some sort of carbon groups, and they will be bases. So any nitrogen with 3 groups attached will act as a base, as a weak base. And so you go from ammonia and water, you produce hydroxide and the ammonium ion, which we will talk about in great detail. So those are the bases. And so strong bases like sodium hydroxide, potassium hydroxide, those will break apart completely into sodium and hydroxide ions. And so it's the hydroxide that makes that a base. And so the neutralization would then take place between the hydroxide and the hydronium, or the H plus from the acid, and to form water. So that's the neutralization. So take a closer look at those examples of bases I gave, the weak bases in caffeine and chocolate, phenylalanine here in chocolate. What we're looking for are nitrogen centers with a lone pair. That's not shown here, but every single one of those nitrogen centers here has a lone pair, and they can each take up a proton. Okay, and so it's the same as the carboxylic acid, same idea. You have a combination or a certain arrangement of atoms, in this case a nitrogen with 3 R groups, some organic junk that does that. And so the sodium hypochlorite is the bleach, which the bleach doesn't have a nitrogen center, but it's still a weak base that will react with water to form hypochlorous acid and then hydroxide. Okay, what else do we have here before I am done with my introduction, which is already longer than 10 minutes. Sorry to disappoint, but bases taste bitter. They feel slippery, right? If you've gotten some sodium hydroxide on the hand, or soap, for example, which is made from lye, sodium hydroxide, can feel slippery, and so that's usually an indication that you have a base on your hand. Oil, it reacts with oils to make soap. Well, there's this actually, the soap making. Conduct electricity, also forms ions, breaks apart into ions, reacts with acids to form salt and water, and then it makes the litmus blue instead of pink. So it's a nice little indicator. You can tell the difference there. Okay, I'm actually going to stop. That's enough of an introduction.